Oh, well, thanks for inviting me down. It's a good opportunity to come and speak. I just thought I'd start by just reassuring Richard, wherever he is, that he was worried that his talk might be a little bit conventional and normal statsy one. Well, you needn't have worried, because I think mine is going to be as well. So the title of Understanding Consumer Preference with Multivariate Visualisation, I guess I'd start really by just maybe explain what I mean by what kind of data I'm talking about. So this slide is just meant to summarise the kind of processes we go through at, say, Unilever and other companies similar to Unilever when it comes to product development. So we might start with, let's find the button, kind of start over here with in the laboratory where we develop new prototypes and products, ingredients, molecules, formulations, and then we might measure the microstructure, physical, chemical performance of the products. So this is a very in-lab process, so the measurements are accurate, low variability types of measurements for the product performance. So then what we want to do then really is, well, how do these products then interact with our consumers? Because our consumers use them. So we want to know how they interact with the products. So then we might move a set of prototypes into the next phase, which might be sensory testing, which is kind of another step away, a bit noisier. The data is, it's a trained sensory panel where people are trained to be able to measure things like coldness or stickiness, things like this. So they're kind of almost linear. So we hope we get quite good data out of that, but it won't be as good as you get in the laboratory. And then what we'd like to do then is then say, well, what about the consumer in home, in use with these products? How do they relate? Can we get information about what makes them prefer products, how they use them? What kind of information can we get about the product properties in use in the home? So what this talk is really going to focus on is, firstly, I'm going to talk a bit about sensory description. Because there's two parts to sensory analysis. There's description and discrimination. The discrimination part is really comparing products. We want to say, by how much is one better than another in loads of different kind of dimensions, like attributes like stickiness or coldness. The sensory description is really, well, can we get scores, profiles for products that we can compare between products? So we might want a whole host of attributes that we measure in a trained sensory panel. And then we want to say, well, can we compare these across products and across sittings and things like this? Another aspect then is to looking at the liking data. This is like a home use test. Typically, you'd have lots and lots more people in home consumer testing, maybe global, regional testing. So I'm going to talk a little bit about the sensory descriptive analysis. Then I'm going to talk a bit about internal preference mapping, and then I'm going to combine the two. So-called external preference mapping, where we try to link the sensory description to the preference. At this stage, we might also take the technical data from the lab and try and relate that through as well. And ideally, what we'd like to do is be able to predict our product preference from our microstructure and our sensory and say, what can we change here to improve liking there? So ultimately, we'd like to be able to do the opposite. Take this and do some kind of optimization back and say this is what we should change in our formulation to get products that consumers like. So we might use some of the Pareto optimal kinds of techniques that Richard mentioned, for instance, there. Okay, so just a quick summary of what I'm going to talk about. So I'm just going to go just through the trained panels, untrained panels, the sensory data aspect, and I'll talk a bit about the preference mapping. So. What have I done? Sorry. Right, so the first thing is product profiling. So this is obtaining quantitative descriptions of the products. So typically, I've just mentioned this, but it's trained assessors. So we have strict panel monitoring, so people are calibrated, if you like, to be able to score. So well-defined scales, usually on, say, 0 to 100, a variable analog scale, so people mark on these things. Usually have good experimental design, so if you've got carryover effects, whereby using one product will affect your in the next product that you use, we can use proper design, like Latin square designs, to try and adjust for that. And also we can compare across sittings. Typical things that you tend to do with this data might be analysis of variance on this, because it is quite well behaved. So things like adjusting for multiple testing, fish analysis across test panels, univariate testing, or maybe even do some multivariate analysis of variance. But of course, often these things aren't really normally distributed. So we'd also like to really interpret it as on some kind of map visually to try and understand the interdependencies between questions and products and how these things relate. Which brings me on to principal component BIPLOTS. Now, I don't know how well known how many people know about principal components? Am I kind of teaching people to suck eggs, or is it something that probably not some people will know and won't know? Okay, that's not too bad. So I was going to say you could do the survey while I talk about it if you've heard of it, but that's okay. So anyway, what is a biplot? What I've tried to show here is, suppose this is our data from our century panel. It's mean-centered, so an average product score would be 0 now on each of the attributes. We want to try and factor it into two matrices, one representing the products and one representing the questions, the attributes. So to perfectly represent, I'll come over here, actually it's probably easier, isn't it? To perfectly represent your data, you'd have to have a P by K and a K by Q matrix where K is at least the rank of this matrix, so that you can then get this product and get our data back. What we'd like to do is get a good representation in 2 dimensions so we can map it, or maybe 3, but preferably 2. So we'd like to find an approximation to our matrix, which we can represent between this product matrix and this question matrix. But we also want to be able to preserve groups of similar products on the map, so we can see which products are being accessed similarly. How the questions relate to each other, which ones maybe correlate, which ones don't. Association between products and questions, so we can relate the two together. And also we want to kind of maintain, if we can, the relative sizes of these differences, so we can kind of get some idea of what the relative differences are, not just whether something's bigger or smaller. So principal component analysis can help us with this. So what principal components, sorry, I have to apologize, it's not quite coming out correctly. So what principal component analysis tries to do is find, it takes your data and it tries to find a transformation of that data to a new data set, such that this data set are all uncorrelated with each other. But more importantly for us, it also gives you them in a particular order, so that the first one it finds will explain the highest amount of variation possible in the data. And then given that you found that first component, as we call it, component or axis, the next one will then find the next greatest amount of variation that you can explain in the data. So the idea there is if you can find this transformation, and we can take the first 2 of these, we can hopefully explain as much variation in just 2 axes and plot them on a nice 2-dimensional plot. So how we find these matrices is really what principal component analysis is about. So as a simple kind of visualization is a very simple 2-dimensional example. So imagine your data looks a bit like that, spread out along the 45-degree line. Your first axis would point that way. That would explain the most variation. So it's not just going there, it's coming this way as well. And then uncorrelated to that would be this axis, which would then explain the next amount of variation. So that would give us these variances, which would be ordered. So the first one would be the largest, the second one would be the second largest. And hopefully these two together is going to explain a lot of variation in the data, so that we can then be quite confident that what we're showing on the map is going to be quite realistic as to what's really going on in the data set. So let's just reiterate what you've said. So if we just break this down a little bit, the P matrix here, if you remember, if I just go back a second actually, if you remember this here, y equals xv, and we've found y with this special v, if we post-multiply this by v transpose and this by v transpose, then that will give us x. So that's what we're using here. So when I was saying x is approximately this y's and these v's, so if we just plot the y's, so now each row of this y will be a product. We've got 5 products, which I've taken the labels off to protect the innocent. And 2 columns, because we've just taken the first 2 components. We can plot them on a graph. So you can see this first axis here is explaining 83% of the variation of the data. That's a lot, that's good. So that's pulling out a lot of what's going on in the data. And the second one's pulling out about 13 or 14%. So that's given us, it's representing a lot of the variation that's present in the data set. So the idea here is that this gives us the product positions, relative positions in the... So we've taken the high-dimensional data and we've projected it down into this 2-dimensional space, preserving the distances between the products. As it turns out, with this particular type of plot, those distances relate to a thing called Malahonow's distance, which is like it's like a Euclidean distance in space, except you scale everything based on the variability in the questions. So it's a bit like an effect size. So here, for instance, B and E are quite close, but that might be because they've got a lot of variability as well. Whereas A is clearly quite different. So we would think that B and E products are actually performing fairly similarly on the panel, whereas A is quite different, and D again is different on this dimension. Okay. If we look at the second part, the Q matrix now, so this is the questions. We might want to, what this gives us is the questions that we asked the assessors scored. So in this particular example, it's actually a deodorant or an antiperspirant. We've got things like tone of colour. I think this is like if it leaves marks on the clothes and things like this. Comfort, glidability, visual texture, evenness of spread. So each of these vectors now is representing how the questions relate to each other. So the thing about it is, because we've used that principal component analysis, it turns out that the cosine of the angle between any two vectors gives us the correlation between, well, approximation of the correlation of the original variables. So for instance, visual consistency and tone of colour are quite close together, whereas something like visual texture and visual consistency are almost perpendicular. If you look at comfort, you've got sheen almost the opposite direction. So the cosine of 0, where they're close together, is 1. That's like correlation of 1. The cosine of 90, where they're almost perpendicular, is 0, so they're almost not correlated very well at all. Whereas if it's -1, say comfort and sheen, it's a -1, so they're anti-correlated. So each of those plots will give us some information about the data set we've collected from the sensory panel. The vector lengths also represent the variance in this case. So there's more variability in this attribute question, whereas in something like visibility, it's quite low variability. So that will show you that as well. So the thing is, these two plots are actually, I'll come back over here now, are actually related. Because our x is actually a product of our y2 and our v2 transpose. So actually, every inner product between a row and a row is a particular point in the matrix. So if we project our y's onto our v's, like that, it gives us a relative ordering of the products in terms of how they scored on that particular question. So in this case, we know that B is scoring the highest compared to A, and then C, which is almost near the average score at the origin. So this leads us to the idea of the biplot. So if we overlay these two plots together, we can get something like this. Now, this is the same data, but I've changed it slightly in that I've scaled the original data. I've normalized the data by the standard deviation. So now all the lengths of the vectors are the same. They're all the same length. They've been scaled greater than 1, just for clarity, but they're all the same length. So we've lost. So it's no longer a Malhammer's distance, it's a Euclidean distance now. So you can see that the products actually have moved a little bit. So I think they've drawn those apart. That's probably because they were more variable before, and now it's not picking that up so much. But anyway, for illustration, this will still give us the same kind of thing. So we can still project onto the axes like that. So if we look at each of the products, you can see that for stickiness, D has the highest stickiness, product D. Now this is the average. A is then the next. C, E, and B are below average compared to the whole set. It's always compared to the set, so you've got to be a bit careful how you choose your set of products in these tests. Equally, we could take another one, like residual look, and do the same thing, project down onto those. Now this instant, we've got E as the highest residual look score on average. Then C and B are quite similar, and then below average, you've got D and A. And also, if we look at the angle between the vectors, we've got residual look and residual feel aren't really correlated very well with each other, so there's no real correlation, so we can tell that from the map as well. These two over here are almost lying on top of each other, so they're very highly correlated with each other. That's tone of colour and visual consistency. And I haven't highlighted it, but if an example might be where they're anti-correlated, might be visual texture and, say, glidability or comfort. Just point in opposite directions. So it's a nice technique in that you can get a lot of information out of your data just on a nice simple two-dimensional map, and you can actually summarize a lot of information in a very visually appealing way. So I'll just reiterate what I've said really. The question scoring scales are calibrated to be linear and continuous in these panels, so that the assessors are trained. So we can always treat them like linear, so PCA is good for linear data. Panelists are trained and checked. The dimension of the data is intrinsically low, so 2 dimensions is a good number of dimensions to represent it. So a biplot is a good way to do that. Of course, if your data is not continuous, or if it's maybe your variability doesn't explain too much variability in 2 dimensions, so you might need more dimensions to really capture the data, then it might not be so good. So what do we do then? Well, there's a general class of models, which Richard actually talked about earlier a little bit, called multidimensional scaling models. So I'm just going to talk a little bit about them. So whereas PCA represents all the data in all the dimensions, and you choose 2, what MDS does is you choose a dimension a priori, number of dimensions. So you say, I want to find the best representation I can of my data in 2 dimensions or 3 dimensions. So in that respect, if your data is really intrinsically higher than 2 dimensions, this might be a better option than principal component analysis. Distances between pairs of points don't approximate original distances now, though. So where you had the Malahonobus distance or the Euclidean distance, now it's more to do with ranking. So what happens, what this particular general form of multidimensional scaling does is to try and preserve the rank order of products or questions in the data. So it tries to, as best as possible, reproduce the rank orders in the full dimensional space in a, say, a 2-dimensional map or a 3-dimensional map, which is what I've just said. So you get a better representation in 2D of intrinsically higher dimensional data, and you can represent non-metric data such as ordered ranks, which you can't do with a principal component analysis. So this is the same data again, but using a non-metric multidimensional scaling. So non-metric meaning that the similarity between the products. So it's the products that we're really mapping. The distances don't have to be a metric distance. So it could be some kind of ranking or some other type of distance. And so again, it reproduces the product relationships. The axes don't really have much meaning in these plots, whereas in principal components you can relate the axes to real things. You can't really with a multidimensional scaling plot, because this configuration you can rotate. You can rotate it around, it's still valid. So what I've also done here is to overlay the questions again as weighted averages of the axis scores across the products. So you can get it's a very similar map to what we had earlier, except now it's about proximity rather than projecting onto vectors, because that doesn't have any meaning anymore. You can't get the ordering, the relative differences. It's just about proximity, what's alike and what's different. So mostly we use train panels to try and do the sensory profile, but there is another method which I thought might be worth mentioning, which is called free choice profiling. So this is a slightly different approach. It uses untrained consumers. There's no need to maintain a sensory panel, so you don't have to worry about checking them and doing panel checking, etc. And it's less resources required to do this. So what's involved in this? Well, the way it works is that people develop their own individual vocabulary, so we don't give them a set of questions that that the assessors have to say, what's this, this, or this. We let them decide on themselves. So they get the product and decide, well, these are the attributes that I think are important for this product. So everybody gets their own vocabulary, and then we get score sheets for these things, for each individual score sheet. And individuals assess their own score sheets, so everybody does their own set of questions. The only thing that you do have to have, obviously, is that everybody must score the same objects. Otherwise, you've got no way of doing anything with the data. So as long as you've got something which is consistent, we're OK. So you can have different attributes and different numbers of attributes as well. So one person might think, oh, there's 4 or 5 things that are important. Somebody might come up with 10 or 3. Doesn't matter. We let them choose. So again, we can use principal component analysis for each individual person's set of questions to get a representation, which maybe you choose a particular number of components. It might not be 2, it might be more than 2, but you choose a given number which represents that particular configuration. And then what's different now is that we use a thing called generalized PROCUSTES analysis, which tries to take each person's scores and fit them together to get a consensus. So the key is the products, because we try and map the products together in each of the configurations. So I don't know if people are familiar with this. The idea is that you take a configuration and you can translate it So they might be in different places. Effectively in space, you can translate, rotate, and scale so they fit together as best as possible. So you try to minimize the sum of the squared deviations between individuals. And in doing this, you also maximize product deviations and the agreement between individuals. So I've got an example here, which is actually in Spanish. So it was a Spanish example, but I've got the English translation, so I'll try and see if I can. So this is the sensory space of the attributes for people for this particular set of, well, what was it now? It was, I think it was hand wash. Have I got the right one? It was like a dishwash detergents. So each panelist, so there's only 5 in the example, so there's 5 panelists who did this, and they all created their own questions. So by projecting onto like a principal component map after doing the PROCUSTES, we can look for areas where maybe they're asking the same things. They may have given them different labels, but they actually talk about the same kind of thing. So we can derive questions from this that we might be able to use again. So just an example up here is creamy and moisturising. I think that's moisturising, if I remember rightly. It's down the list there. Anyway, that's kind of creamy moisturising questions. Over here we've got light, smooth, and opaque. The product's light, smooth, and opaque. Affordable, foamy, thick, abundant, consistent. So you can see you might be able. It's a bit muggy, but you can pick out where people are really, well, hopefully they're meaning the same thing, even though they may have labelled it differently. So. And again, this is just a product map now. So this is taking the consensus plot. So everybody's configurations are being mapped together, and then this is then the consensus for the products mapped into, again, a 2-dimensional map. So in this case, I've got some confidence intervals on there as well. So similar to the BIPLOT, we can see which things are similar, which groups look the same, which things are different. So that's free choice profiling. So anyway, now let's talk a bit about consumer preference. So what is it? It's really developing models of preferential choice. So the data score is usually ranks of preference. So which ones you're ranking them maybe, or you might have a scale. But often it can be ranked, so you rank them from which one you prefer to the ones you prefer least. Again, this tends to be untrained consumers, so it's not like a panel. So the data is a lot noisier. There's some assumptions you have to make. So different individuals perceive products in the same way, hopefully, but individuals might differ as to what an ideal combination of the product attributes are. So it's that combination of the attributes that we're trying to understand that people see differently. We have to make the assumption that they're interpreted in the same way. There's internal preference mapping, which I mentioned earlier, which is really looking at just the liking consumer data. So we might be looking for clustering, how consumers cluster around products. So typically a data matrix will be products by consumers. And then there's external preference mapping, where we want to predict the maximum consumer acceptance for a set of prototypes based on maybe the sensory data we've collected. So we might have 2 different sets of people, sensory panels, consumers, but we'll have the same products. Can we link the 2 together? So the sensory data in this context is the external data set. So what we're trying to do is relate them on a common underlying scale. We locate individuals with products as points in a joint space, so again, consumers and products, a bit like with the map we looked at earlier. But what it's trying to say is that individuals will pick products closest to what their ideal point is. So the ideal point refers to what their preference would be, what they would prefer the most, their ideal point. So one way of doing this is a method called multidimensional unfolding, which is another MDS method, but it's slightly different. So I just thought I'd try and give a quick example of what this entails. So imagine this kind of toy example, which I took from this book down here. We've got 2 judges. You've got essays, A, B, C, D, E, which have been judged by these judges and ranked in order. So first, second, third, fourth, fifth. So Judge A thinks B was the best essay and D was the worst. Judge 2 thinks A, D again. So you can imagine that. So the idea of the unfolding is to find a common scale which represents all this information. So if you look at the way this works here, it's called unfolding. That if you see this is where Judge 1 is on the scale, if you fold that line, that point, it reproduces these rank orders. So you should get B, C, A, E, D, B, C, A, E, D. And for judge 2, if you fold there, you should get their rank order of A, B, C, E, D. So that's the kind of idea. So if we can represent the consumers and products on a two-dimensional map, maintain as accurate as possible all the ranks across, maybe it might be a whole number of judges or attributes, then that's the idea with unfolding. So this is an example taken actually from an R package called SmackOff, which is it's got this data set in. So this has had an unfolding occur. So you get, for instance, here you've got, I think that's toast with marmalade. So people are asking to order breakfast items, based on their preference, 42 people. So you've got, for instance, toast with marmalade and buttered toast are very similar. So because they're close on the map, their preference scores across all the panelists are very similar, indicating where they're being ordered. You might look at the panelists. So you've got a big group of panelists here, all around Danish pastries. So they are all got a high preference. So Danish pastry would be their highest preference. So it's a nice way of mapping out the preference scores and the ranks. I mean, I guess you could look at, say, I think that's jam donut and glazed donuts are very similar. Maybe not surprising. Whereas this corn muffin's down here on its own are not particularly well liked. So it's a really nice way to visualize this kind of data without... So anyway, the external preference mapping is where we're trying to now link the sensory panel to another set, say the in-use, the home use testing, consumer data. So the data is usually, what we basically do is you take the sensory space, the data that we've got taking the principal component, and we try and just basically regress that onto the liking scores from the consumer test, and then try and predict from the sensory what the liking might be. So it's usually sensory. The sensory data really has to have some kind of prioritization for consumer preference. So it must pertain to preference, otherwise it's not really going to make any sense. So it's got to be something in there that says, will direct preference in the consumer. So again, we could use a pre-CA, principal component analysis, to create the product sensory map. And then we can regress that onto the preference scores, usually using, well, you wouldn't use a linear model because you just get a plane. So we usually use something like a quadratic model or a response surface kind of model, so we can try and find optima and preference points where you might get maximum liking. So nice as an example taken on conditioners. Actually, these are hair conditioners. Each point will be a consumer product point. So that will be what a consumer has assessed a particular conditioner. Each person does all the conditioners. That has to be the case. So everybody has to have done everything. Red is high liking. Blue is low liking. So what's interesting is that what we've pulled out really is that there's two groups of products. The first axis along here is pulling out a difference, and then also the second axis is pulling out a difference. So we've got, for instance, these products here which are similar, liked for similar reasons, maybe. Then over here we've got another group which have high liking, but for different reasons to this group. And in practice, what we can do actually is you could drill into this data and see, well, what's the profile, what's the sensory profile? Or you can actually overlay the sensory attributes on as well to see, well, maybe this direction is where this particular sensory attribute is high. So maybe that's the thing that might be. It's not so much, it's not predictive, and it's almost not, you've got to be careful because these things interact. So it's almost giving you an idea of where you might go. Where you might then you might say, well, this might be, if we want to change one thing that will get us up here, maybe we change this attribute. So, I mean, the final thing I wanted to talk was just drivers analysis. So we've seen how you might be able to map out your data with correlational. It'd be nice to be able to actually understand the structure a little bit more in the data. So what I mean by that is, rather than just look at the correlations, maybe there's some relationships that we can pull out, things that relate to other things, but not so much in a sort of structured way, like with a graph. So, I mean, typically we would do factor analysis, actually, and regression. So factor analysis is like principal component analysis, except we're looking to try and find these so-called latent variables. So our factors now, our components now, represent new variables that we want to interpret. So the idea is that our observed variables are independent, given that we know these. So we can then kind of try and express our data in terms of these variables rather than these. So we call them factors. And then we could regress those factors onto the overall liking. So what I really want to talk about was graphical models. Graphical models are probability models, except combined with a graph. So the idea is that we want to model the probability distribution of our data, but we want to be able to visualize it as a structured graph, which might give us some more insight into what relates to what, rather than just the correlations. So it consists of a data plus a probability model. So each of these graphs, you can get a likelihood function and compare them, so you can get the most likely given your data. The key concept is this idea of conditional independence. So if you imagine this is a covariance matrix for, say, just two variables, it seems as though they're all, actually it should be three variables, shouldn't it? Sorry. Yeah, anyway. The idea being is that there's high correlations here. There's three variables. This should say three variables. It's a mistake. But they all seem to be highly correlated. If you look at the normal marginal covariances. But if we look at the inverse covariance matrix and the partial correlations here, actually this is the kind of structure that we've got. In that, given that we know x1, we can say that x2 and x3 are actually independent. So it's this conditional independence idea, and that's the kind of basis of this graphical modeling. So that's quite. So if you look at the actual value there, it's quite low. So it's actually suggesting that the partial correlation there is low between these two variables. And this is the crux of it. So if you've got a joint distribution between two variables here, conditional on another one, then you can split it into two separate probabilities. Probability of x2 given x1 and x3 given x1. So we can start to break it up into this kind of graphical structure based on the probability. So rather than having a joint probability distribution, we can split it up into these products. And the nice thing about this is it holds for sets of random variables as well. So if these were sets rather than just single variables, then you can say this set is independent of this set if you know what the values of this set is. So you can do these kind of conditional independence inferences. So just an example. This is 3 questions from it's shampoo. Set means shampoo and conditioner. So you've got let's just see if I've done this. So you've got fairly high, well, not really high, but you've got reasonable correlations here and here, 0.5 and 0.6. But if you look at the partial correlation, it turns out they're actually not that high, 0.2 and 0.1. So what's probably going on there, even though the correlation structure looks as though they're all very highly correlated and related, is maybe it looks more like that. So maybe moisturize your hair these two are conditionally independent, given that we know that moisturization of your hair is the variable. So if we know this, we can predict this without knowing that. Or we can predict this without knowing that one. So it gives you this independent structure. So what's the advantages of doing this? Well, conditioning's the key. It allows us to give a visualization of the structure of the data, not just the correlations. Also, another nice thing about it is that it unifies different types of variables. So not just continuous variables. You can also combine it with contingency tables, categorical variables into single maps. So as an example, this is a hand wash bar example. It was actually in India. So we've got 10 commercially available laundry bars, which are in the actual study. We were interested in trying to change the formulation at the end. 19 panelists, 32 attributes. And the thing was, we had like 2 locations, one with soft water, one with hard water. And we wanted to see, can we find out what drives the liking of the bars in these 2 regions, and can we find a formulation difference that might differentiate them? So we might put one formulation in one place, another formulation in another. So to do that, the first thing we did was to reduce the number of variables, because we've got like 32 attributes. So we did a factor analysis. So this is a representation of factor analysis. So we've got 5 factors, and what this is these are the highest correlated variables with those factors from our the questions that we asked. So like soapiness, dryness, hardness. The way we got this was by rotating them to try and align the factors with the variables, which is a common method they use with factor analysis. But what it does do is induce correlation between these as well, because before they would have been uncorrelated, which would have been much use. So then we try to label these as what they might mean. So this is clearly maybe a perfume factor, a grip economy, or a grit, or an engagement factor. That one's a bit more messy, but we can't call it engagement or tactile feel. There are issues with doing this kind of thing, but that's not the talk, because you've got lots of variables which we're not including, which together will actually are important. So just labeling them this way actually is something that you probably should avoid, but it's commonly done. Anyway, so this is a graphical model of that data. So you can see we've got the preference scores in each location, and we've got each of the factors which have now been put into this graphical model. So what we've done is we started probably by put normal links in between everything, and through a kind of stepwise process, a bit like regression, you take out the link which is least important, given some criteria. So you do likelihood ratio tests basically, and then you end up with a map which has only got the important connections in the graph. So the thing that we noticed, which was amazing, was that although let me see, so you got engagement connected to both. So the engagement factor was important, but there was differences. So for instance, the tactile feel was the red is positive correlation, the blue is negative, by the way. So the tactile feel was also important for this location, but not for this one. Whereas the grip economy of the bar was more important here. So you could kind of say that given that we know this and this, we can predict this for this location, but for this location we need engagement and tactile feel. So from that, we were then able to go back to the formulation and map and see what part of the formulation we're actually mapping to these kind of preferences. So it actually ended up with new products in both areas. So that was it. This is just a few resources. If you're interested in doing kind of BIPLOTS and mapping type things, Sensor Miner in R is very useful, as is SmackOff for doing unfolding. And then for graphical modeling, there's R packages, but also I've used this thing called MIM, which is a free program. So, thanks.